In this video, I want to look at homomorphisms between rings. So let's consider two rings A and B, and I want a function f going from A to B. So what do we need for this to be a homomorphism? Since rings are also groups under addition, I want this to be a homomorphism under my group operation. So f of x1 plus x2 should be equal to f of x1 plus f of x2. Let's suppose we have a homomorphism from A onto B, so specifically a surjective homomorphism. Then B is known as a homomorphic image of A. Another thing about homomorphisms, if we have a homomorphism F from a ring A to a ring B, not necessarily injective nor surjective, then the range of this homomorphism is a subring of B. So the range of a ring homomorphism is always a ring. And the range of a homomorphism is always a homomorphic image of its domain, since that would be onto. So intuitively, if B is a homomorphic image of A, this means that certain features of A are faithfully preserved in B, while others are deliberately lost, just like this was true in terms of groups. So let's look at some examples. Let's consider the parity ring P. So this ring consists of two elements known as E and O. For their addition, we can build their addition table. E plus E is E, E plus O is O plus E is O, and O plus O is E. For multiplication, we can also build this group table. Once again, or this ring table, we also have E and O. E times E is E times O is E, O times E is E, and O times O is O. So if I build a function f going from Z to P, which takes even integers to E, odd integers to O, this would be a homomorphism, since it's easy to see that this is E stands for even and O stands for odd, and this is how we add even and odd and multiply even and odd. So this would be a homomorphism. Before we do a few more examples, let's talk about a couple of more properties of these homomorphisms, starting with the kernel. We're going to let f be a homomorphism from A to B. The kernel of my homomorphism f is the set of all x in my set A, such that f of x is equal to 0. So it's the set of all elements of A which are carried onto the 0 element of B. So this is very, very similar to the ideal of the kernel of a group homomorphism. And it's actually a very important fact that the kernel of f is an ideal of A. So let's show that this is true really quickly. We have an element x belonging to my kernel, and an element A belonging to my ring A. Well, f of xa is the same thing as f of x, f of A. F of x is 0, and 0 times any element is 0, so this would still be in the kernel. So this does absorb products, and it is an ideal. We can also extend this idea of homomorphisms to isomorphisms. Let's let H be a function from the real numbers to the set of all 2x2 matrices with real entries, defined as H of x is equal to the matrix x0, 0, x. I want to start by showing this is a homomorphism. So let's consider hx plus y. This is, by definition of the function, x plus y, 0, 0, 0. Matrix addition says I can break this up as x0, 0, x plus y0, 0, y, or y0, 0, 0, which is by definition hx plus hy. In order to do the multiplication, let's start with hx, hy, since this will be a little bit easier for us. Hx is x0, 0, 0. Hy, y0, 0, 0. And if we multiply, we would have xy plus 0, 0 plus 0, 0 plus 0, and then finally 0 plus 0, which we can see is by definition h of xy. So this is definitely a homomorphism. Let's consider the kernel. Well, we want all real numbers that would map to the 0 matrix, 0, 0, 0, 0. So that just considers of the element 0. What about the range? Well, the range of x is all of the matrices of this form, x0, 0, x, or x0, 0, 0, such that x is a real number. I can make the first entry in this matrix whatever I want, but the others will always be 0. Let's let R cross R be the set of all ordered pairs of real numbers with the usual addition, and we're going to define multiplication a little bit differently. AB times CD is going to be equal to AC times BC. And we're going to call this set R cross R with these two operations A. Let's let F be a function from A to M2 of R, so the set of all 2 by 2 matrices with real entries, where f of x comma y is equal to the matrix x0, y0. And I want to start by showing this is a homomorphism. Let's start with f of AB plus f of CD. F of AB would be A0, B0. CD, f of CD would be C0, D0. I can add these two to get A plus C, 0, B plus D, 0, which is exactly f of A plus C comma B plus D, which is exactly what I need for my homomorphism. For the next piece, let's look at f of AB times f of CD. Well, this would be A0, B0 times C0, D0. That would be AC plus 0, 0 plus 0, BC plus 0, 0 plus 0. This is, by definition, f of AC comma BC. And if I look at my group operation up here, that's exactly what I needed it to be. So yes, this is a homomorphism. What about the kernel? The kernel of this thing, we're going to need f of x comma y to be equal to the 0 matrix. So we would need both x to be 0 and y to be 0. So the kernel is just the origin 0, 0.